Okay, so good morning, everybody, and we're going to try and finish our section on endocrinology. I'm sorry, not immunology, endocrinology. And to start off, I just want to remind you, please, that first of all, you have a test next week, which your revision should be well along the way. That test will go up to the end of today's class, end of today's recorded class, okay? The end of the endocrinology. So it's mainly going to be immunology and endocrinology. So before you do anything else, I want to make sure that you understand that you are to revise this section. That is insulin and glucagon control of blood glucose via the activity of the endocrine activity of the pancreas. There are several slides that follow this particular slide, which are now hidden in my presentation, but which you can open if you go to the PowerPoints loaded to Canvas. You are pleased to revise that carefully. You will be asked questions about it, so make sure that you do that. Okay, so we are going to start now to discuss in detail the activity of the hypothalamus and how it integrates with the activity of the pituitary, and then globally with various other organs and endocrine organs throughout the body. The hypothalamus is often referred to as being the conductor of the body's orchestra, because it monitors so many different functions and then issues hormonal commands to control those functions. So this is a complex interaction of the hypothalamus, which is part of the nervous system, with everything else in the endocrine system, and then with the organs of the body. So I showed you on a model in class. The hypothalamus consists of the walls of the ventricle, of the cerebral ventricle, down here right at the very bottom. And it's a very, very small area of the brain. It is nervous tissue, it's part of the brain. And it also has input from sensory nerves. In itself, it has some sensory capability, but it has input from much further away in the body through sensory nerves. And this is the way it monitors what is happening. It also can monitor the status of body fluid passing through it. And the responses are the effects are from responses of the hypothalamus to that information. But it is not really a direct release of hormone to the body, so much as it is an interaction between the hypothalamus and a tiny gland associated with it, one of the most powerful endocrine glands in our body, which is the pituitary. The pituitary produces many, many different hormones, which have very powerful effects. So the pituitary sits below the hypothalamus here. It's divided into two parts, the anterior and the posterior. Now just get the orientation correct in your mind, because here's the brain facing that way. Forward is that way, okay? And you can tell that because you can see this very distinctive part of the brain, which is the cerebellum, and that is always at the back. So this is pointing, the person facing that way. So this is the front part, or the anterior pituitary. This is the back part, or the posterior pituitary. And they are, in fact, quite different to one another. And the anterior part here is still part of the brain. It is nervous tissue and richly invested with nerves which actually originate in the hypothalamus. This part here is completely different. It's actually glandular, and it is derived in the fetus, derived from epithelial tissues. And so it's completely different, but it communicates very, very strongly with the hypothalamus, as we'll see in a minute. The two halves produce completely different kinds of hormones. So Here is the anterior. Now we've switched around. Now the person's, to confound us, is now facing this way. So here's the hypothalamus, here's the anterior pituitary, and here's the posterior pituitary. And I believe that this orientation now is preserved in all of our other diagrams. Whenever you look at a diagram of the hypothalamus and pituitary, make sure you know which way the orientation lies. So the posterior pituitary produces two major hormones, and these are ADH, that is Antidiuretic Hormone, and Oxytocin, that we have already heard about. So the posterior pituitary is actually part of the hypothalamus in a way, because here are the hypothalamic nerves there, and these are neurosecretory nerves, neurosecretory cells, and so they're not communicating a nerve impulse. Instead, they are manufacturing hormones. They're manufacturing ADH and oxytocin, and that is temporarily stored here in the posterior pituitary before it enters the blood vessels and is distributed through the body. So these nerves now are running all the way from the hypothalamus all the way here into the posterior pituitary, where they release their product. So these two hormones, this is antidiuretic hormone, hence ADH. A diuretic is something that makes you urinate more. You lose fluid with a diuretic. That's one of the reasons you pee so much when you drink beer. Okay, it is strongly diuretic. But an antidiuretic will stop the kidneys from voiding so much fluid. This has two major purposes. The first is when you're short of water, you're thirsty and everything, then you produce a lot of ADH to conserve as much water as possible. But there's another really important function for ADH, and that is it is involved in the regulation of the blood pressure. Because by retaining water, it can put that water into the blood vessels and increase the blood volume, and that will raise the blood pressure. Okay, so that's two important functions of ADH. Oxytocin, we have already heard about. It actually has widespread effects, but the one that we talked about was the pumping of milk in the breast. It acts on smooth muscle, and it causes contractions of the smooth muscle, which will pump milk. It also has an involvement in labor and acts on the smooth muscles of the uterus to increase the cramping of the uterus during the birth process. Both of these processes regulated by feed forward or positive feedback. So that's a distinction of this particular hormone. So these are termed non-tropic hormones. And a non-tropic hormone is a hormone which acts directly on the body without passing through an intermediary endocrine gland. We're going to see now that very frequently there may be a cascade of hormones, one endocrine organ talking to another endocrine organ before a final non-tropic hormone is released to effect a result in the body. So a non-tropic hormone is a direct action. The hormone is released, it has its effect on a particular organ. Get it clear in your mind, the structure of this posterior pituitary, how it links with the hypothalamus, and remember it's two different hormones. Okay, so now we're going to go have a look at the anterior pituitary. Anterior pituitary, much more diverse than the posterior pituitary. And it produces its own sets of hormones, but it does so under the control of the hypothalamus. The hypothalamus produces a wide range of hormones which act either to cause the release of anterior pituitary hormone or to stop its release. If it's causing the release, it's called a releasing hormone. If it stops it, it's an inhibiting hormone. And so there's a simple example. There is a hormone which is produced by the anterior pituitary, which is called prolactin. Prolactin is the hormone which causes the production of milk in the breast. So it interacts with oxytocin because prolactin causes production of milk. Oxytocin promotes its release. But this prolactin hormone is released from the anterior pituitary under the instruction of the hypothalamus. And the hypothalamus produces prolactin releasing hormone that acts on the anterior pituitary, and the anterior pituitary then produces milk. So what is happening here is we've got an endocrine organ, the hypothalamus, producing a hormone which acts on another endocrine organ, which is the pituitary. That the endocrine organs chattering to one another, that is by use of a tropic hormone. Those releasing and inhibiting hormones are tropic hormones because that is the way the two endocrine glands converse with one another, if you like. Okay, so don't freak out. This is quite logical. The anterior pituitary produces many different hormones. And it is closely tied, of course, to the hypothalamus. So let's just have a look at some of the actual anatomy of it. These are the neurosecretory cells of the hypothalamus. And these are the cells now, this tract is what is going to interact with the anterior pituitary, which is here. You remember in the posterior pituitary, the nerves ran all the way down. In the anterior pituitary, they do not. They just, here's the wall of the hypothalamus surrounding here, and embedded in it are these neurosecretory cells. But they actually secrete their hormones into blood vessels. And those blood vessels carry the hormones to the anterior pituitary. Now, I'll just remind you of something. Any blood vessel system which communicates directly between organs without passing through the heart is called a portal vessel. So these are portal vessels. They run directly from the hypothalamus to the anterior pituitary. And they carry releasing or inhibiting hormones, which are going to act on the glandular tissue of the anterior pituitary. So here are the hormones from the anterior pituitary that we are going to mention. The hormone names up here, targets are listed down here, and I'll just now and again mention an effect or two of them. So the first lot are follicle stimulating hormone and luteinizing hormone. The full names are given to you up here. FSH, follicle stimulating hormone, LH, luteinizing hormone. These are tremendously important in reproduction because they are produced in both men and women, but they have their effect on the gonads. In women, they are the primary way in which the menstrual cycle, the fertility cycle, is regulated. In men, they govern the release of testosterone and the development of sperm, the production of sperm. So both of them closely involved with reproductive features. So there's follicle stimulating hormone and luteinizing hormone. These two, as with all of them, they are produced under the influence of releasing hormones, follicle stimulating, releasing hormone, luteinizing, releasing hormone. So That applies to all of these. They have their own releasing hormones. They also have their own inhibiting hormones. And this is how the hypothalamus controls their levels. And the hypothalamus controls those levels in response to information it is gathering about their effects. These are mostly regulated through negative feedback. Occasionally, there are some which may be positive, but most of them are negative, regulated by negative feedback. And then through the activity of releasing or inhibiting hormones from the hypothalamus. This is TSH, easy to remember. This is thyroid stimulating hormone. And again, this is released under the influence of a releasing hormone. This one, a little bit more difficult to remember, and but make every effort because it's an important one that we'll talk about in some detail. This is Adrenocorticotropic Hormone. Here it is here, Adrenocorticotropic Hormone. Okay, thyroid stimulating hormone there. All of these here are tropic hormones. So they're going to act on other endocrine glands elsewhere in the body. They're going to have their effect on those glands. They're tropic hormones. We'll see how in a minute. This one here, prolactin, I've already mentioned. It governs the production of milk. That is a non-tropic hormone. There is another one, MSH. We're not going to worry about MSH. This is melanocyte stimulating hormone. It has various effects, but the most important thing is that it's involved with regulation of our sleep-wake cycles and things like that. But we're not going to talk about it. The prolactin is important. MSH, don't worry about it. The last one is growth hormone. And growth hormone has both tropic and non-tropic effects because growth hormone has almost global effects throughout the body. Growth hormone not only regulates growth in terms of height or whatever, it is also involved in cell division and things like that. It has many, many effects throughout the body. It's a very, very important hormone. Okay, so what I want you to do, I want you to draw up a table and make a note, not only of the names, the full names, the abbreviations, the target organs, and their main effects. There are several slides here which give you all the detail and more than the detail you need. But make sure that you go through these, understand at least for all of these hormones except MSH, what their major effects are, what their major target organs are, etc., and whether they're tropic, non-tropic, etc. Okay, so let's have a look at typical kind of interactions. Many of these hormones, especially the tropic hormones, lead to hormone cascades. That is, several endocrine gland systems may be involved before a final effect is reached. And one of the important reasons for that is that it allows for amplification of the signal. So thyroid hormone is a typical cascade system because it involves the release of hormones from the hypothalamus, the anterior pituitary, and then the thyroid gland. And then what the thyroid produces has a global effect on the body. And these cascades are almost always controlled by a powerful feedback system, a negative feedback system. So here's how the thyroid cascade works. Remember what I told you, that the hypothalamus receives information from sensory neurons. Now it has its own sensory neurons, which monitor body temperature, the body temperature of blood passing through it, and body fluids surrounding it. But it also receives sensory input from distant neurons. Your feeling of being cold actually communicates to your hypothalamus as well. And when that happens, when the hypothalamus senses the falling body temperature, particularly of the blood, it releases this. It is called thyrotropin releasing hormone. It is obviously, it's a releasing hormone. This hormone is released into the portal blood vessels, and it travels to the anterior pituitary. So that's, here's our one endocrine gland. Here's our next endocrine gland. So this is tropic. The anterior pituitary now releases its own hormone, and this is TSH, or thyroid stimulating hormone. Its name tells you everything you need to know. It travels through the blood system. Remember, it's going to be distributed throughout the body, but it only has effect on the thyroid, which lies here right below your Adam's apple. The thyroid then releases a hormone, which is extremely powerful. Actually, it's a set of hormones, but we just refer to them as the thyroid hormones, or sometimes they call it thyroxin. And so here they are here. These are the endocrine cells of the thyroid, and under the influence of thyroid stimulating hormone, they release their hormones that we refer to as thyroxin, or the thyroid hormones, which now again travel globally. But now many cells of the body are sensitive to the presence of these thyroid hormones. In fact, it is one of the most important ways in which our body regulates our metabolism. And when the cells perceive these thyroid hormones in the body, they increase their metabolism. So that when you're cold, that has the important effect that you generate more heat. You begin to respire more, for example, in the cells, which generates more heat. It's a waste product of all of the metabolic processes. But of course, in animals like us, which maintain a constant body temperature, it is very useful because we can use that to keep the body temperature in a homeostatic balance. The way in which that happens is that as the body temperature rises, there is a very strong feedback, but it's a twofold feedback. It's a feedback first on the anterior pituitary. So the anterior pituitary becomes much less sensitive to the releasing hormone, but it also feeds back to the hypothalamus itself, and hypothalamic activity decreases. So it produces less releasing hormone. Anterior pituitary is less sensitive, so less thyrotropin, or thyroid stimulating hormone, is produced, and less thyroxin, or thyroid hormone, is produced to raise the body temperature. This is how this system maintains homeostasis as far as temperature is concerned. And it's a typical cascade. Now, the thyroid is an interesting system because it actually consists of two glandular systems. There's the thyroid itself, which is a large, I thought I had a picture, but I don't. It has a large butterfly-shaped gland, but on the back of the thyroid, there are 4 tiny little glands called the parathyroids, and they actually they really have very little to do with the thyroid at all. And they are responsible for producing parathyroid hormone. And that is released by the parathyroids themselves, but it interacts with another hormone produced by the thyroid gland called calcitonin. And the two of them, in fact, interact throughout the body together with vitamin D to regulate blood calcium levels. In the bones, for example, we have a huge store of calcium. If our blood calcium levels begin to fall, we need to access that store of calcium to raise the blood calcium again. And it is done through this interaction, the interaction of parathyroid hormone and calcitonin. So I have set you this as a piece of homework. This can come into me after Easter, after the Easter weekend. And I want you to redraw the figure that follows this, open up the hidden slides, of course, as you should always do, and redraw that figure and provide an explanation of the interaction. It's basically an interaction of thyroid, parathyroid, the skin, and the bones, how that all interacts to regulate blood calcium levels. Okay. We, meanwhile, are going to talk a little bit more about the adrenal glands. We've already mentioned adrenal glands and adrenal function because I've talked to you about the fight or flight response, which is a short-term response in response to sudden stress. But in fact, the adrenal glands are a lot more interesting than that, than just having the one function. They have many functions. And in fact, they're like a double glandular system. They have the adrenal glands sit on top of the kidneys. Here, the kidneys, here, the adrenal gland there. And on the outside, there's one kind of tissue, which is the adrenal cortex. And then in the interior, there's the adrenal medulla. And it's the adrenal medulla, actually, that we've talked about before, because it's the adrenal medulla that produces adrenaline and noradrenaline, which produce all of the effects of the fight or flight response. But in fact, the outside of the adrenal gland, the adrenal cortex, is also involved in stress responses. So the response to stress is tremendously important. It has enormous survival value through evolution. And in one form or another, in fact, some sort of fight or flight response exists right down to single cells. They run away from predators, etc., all the way up to us. And it's a complex produces a complex interaction between hormones, the whole of the body, and especially with aspects of the nervous system. That is, they interact with parts of the unconscious, involuntary nervous system, which is called the sympathetic and the parasympathetic nervous system. We will hear more about that when we talk about nerves and the nervous system. But for the moment, let's just have a look back at that short-term fight or flight response that we saw before, and see where it's actually coming, where this the hormonal basis of this lies. The first is that the hypothalamus can communicate with the rest of the body through a set of communicating nerves called the cranial nerves. And in response to something like a sudden fright or something like that, first of all, you get a reflex response, a startle response, where all the muscles, you jump, literally, you're preparing, in fact, to gather your muscles together for flight. Very quickly, the hypothalamus sends a message through a reflex system to the adrenal gland. This nerve here communicates with the adrenal medulla, the interior of the adrenal gland, and it produces all of the effects that we've already talked about. Glycogen gets broken down into glucose and released to raise the blood sugar levels. The blood pressure shoots up because blood vessels constrict in some areas to shunt blood into other blood vessels, which dilate to deliver blood to things like the muscles, which need a lot of fuel and a lot of oxygen to work. The breathing rate goes up, the heart rate shoots up, the metabolic rate shoots up. All of these effects are due to the release of these two hormones, epinephrine and norepinephrine, very, very similar to one another. And we refer to them in common parlance as adrenaline, simply because they come from the adrenal glands, but they're actually two hormone systems. That is a response to short-term stress. It does not last long because this impulse, this nerve signal doesn't get repeated, okay? But instead, you realize that under long-term stress, if the organism is continually, repeatedly stressed, and especially if it is subjected to long-term, lower grade stress, something else comes into play. And this is the activity of the adrenal cortex. This is again under control of the hypothalamus and of the anterior pituitary. Under long-term stress, that is, it can be anything. The poor people in Ukraine, for example, are probably all suffering from this long-term stress. And what happens under those kinds of circumstances is that the hypothalamus releases a releasing hormone called adrenocorticotropic, a releasing hormone which goes to the anterior pituitary, which produces this hormone, Adrenocorticotropic Hormone, ACTH. Remember, this is produced in response to stimulus from the hypothalamus, from the releasing hormone. That this substance, Adrenocorticotropic Hormone, what it tells you, it's a tropic hormone. It communicates from the anterior pituitary to the adrenal gland, but to the outside of the adrenal gland, to the cortex. And that the cortex produces a set of hormones which are called the corticoids, named for the place they come from, the corticoids. So here we have our long-term stress. Hypothalamus produces a releasing hormone. Anterior pituitary produces ACTH, Adrenocorticotropic Hormone, which travels via the bloodstream to the cortex. Remember, the adrenal medulla was stimulated directly by a reflex nerve from the hypothalamus. The adrenal cortex then secretes corticoids. It's not just one, but we can just call them the corticoids. And these produce very interesting effects. First of all, they increase the blood volume, they keep the blood volume up, and they increase the blood pressure. They also result in the retention of sodium ions and water. Both of these contribute to increased blood volume. They continually, at an elevated rate, break down glycogen and also increase the breakdown of glycogen to maintain a high blood sugar. There are many effects, but I only mention the last one here, which is that they suppress the immune system. Now, this is very, very interesting. If this was just for, this is almost like that short-term stress, but this is lasting over a long term. You can see some similar things: increased blood sugar, etc., increased blood pressure. And this here, the suppression of the immune system, is tremendously important. People who continually release these corticoids at a high level are very, very susceptible to diseases of the blood circulatory system, high blood pressure, heart damage, heart disease. The increase in circulating fats leads to an increased risk of atherosclerosis, or coating of the blood vessels, which can lead to blood clots, which can lead to heart attack, stroke, etc. And this suppression of the immune system leads to an increased propensity for infection, and also an increased propensity for cancers. Because remember, the cytotoxic T cells and other elements of the immune system, one of their principal responsibilities was to seek out potentially cancerous systems and kill them. Instead, that is now suppressed. This is the effect of long-term stress, of living. This is your businessman who's hungering for the next $10 every minute of the day, right? These are people living, this is your hospital worker treating hundreds of COVID patients. These are people living under stress, continual stress, which is unrelieved. And this system becomes endemic, if you like, in the body, and has had a drastic effect on the lifespan of somebody who is not dealing with the effects of this long-term stress. It's something to really be aware of. Okay, so now let's leave that aside and talk for a bit about the sex hormones, because this is a very, very complex system, again, of interactions between hypothalamus, pituitary, and then the tissues of the gonads. In both men and women, there are very complex interactions, but the primary interaction is with hormones released from the anterior pituitary called luteinizing, LH. Luteinizing means turning things yellow or golden, and you'll see why it gets that name in a minute. Luteinizing hormone and follicle stimulating hormone. Again, they are produced in response to a releasing hormone from the hypothalamus. And this is a releasing hormone called gonadotropin releasing hormone. That is produced by the hypothalamus and leads to the production of LH, luteinizing hormone, and FSH, follicle stimulating hormone. Remember those three names: gonadotropin releasing hormone, and luteinizing hormone, and follicle stimulating hormone. So let's just think for a minute about like reproductive development. First of all, these are going to have their effect on the gonads, on the testes in the male and on the ovaries in the female. So in actual fact, you begin to produce the gonadotropin releasing hormone when you're about 7 or 8. So it travels to the anterior pituitary, and let's just take males for a start. It will get the male testis, even at 7 or 8, it gets the male testis to start to elevate testosterone levels. You always have a certain amount of testosterone present right from birth. But this now is going to start pushing this testosterone level. But there's something really important, and that is that the hypothalamus, in actual fact, is exquisitely sensitive to the levels of gonadotropin releasing hormone and testosterone. And it just will not allow the production of testosterone to occur. There's a very strong feedback to the hypothalamus, which does not allow the body to produce abundant testosterone. It is just simply a matter of the sensitivity of the hypothalamus and the pituitary to the presence of testosterone. The same thing really applies to the ovaries as well. They will begin to produce estrogen, but the hypothalamus is exquisitely sensitive to the presence of the estrogen and stops the production of gonadotropin releasing hormone. So the estrogen levels never rise. So it's a sensitivity of the hypothalamus that keeps the young person pre-puberty. Pre-pubertal is the phrase. Then suddenly, anywhere between, some people earlier than others, 12 and 14, somewhere around there, All of a sudden, the hypothalamus loses this sensitivity. This feedback mechanism no longer works, as it always works to a certain extent, but it loses its sensitivity. And now the hypothalamus begins, in a great burst, begins to release gonadotrophin-releasing hormone, which produces masses of luteinizing hormone, follicle stimulating hormone, and now that can exert its effect. And its major effect is to ramp up the production of testosterone in the male and the production of estrogen in the female. And those rising levels of sex hormones in the boy or the girl are what produce the effects of the onset of puberty. Suddenly, they begin to develop all of the secondary sex characters, which characterize the adult. And this has a very powerful effect, for example, on the release of growth hormone from the anterior pituitary. There is a growth spurt at puberty. Sperm production begins in the male, and egg production doesn't begin in the female. All of the female eggs are sitting in the ovary, ready. They were laid down in fetal development, just as a matter of interest. But what does begin to happen is that the housing of the eggs begins to change, and we begin to see the development of ovarian follicles. That is the development of a unit which contains the egg, which develops around the egg, initially to nurture it, finally to expel it, and then to retreat and become an endocrine organ all of its own. So all of the secondary sex characters develop as a result of the loss of sensitivity to testosterone and to estrogen by the hypothalamus. So the luteinizing hormone and follicle stimulating hormone in the male testes, I'll do it in a little bit more detail in a minute. They govern the production of sperm, first of all. And second of all, they govern the production of testosterone. Those through two different cellular systems. So the follicle stimulating hormone, luteinizing hormone, have their activity on different kinds of cells in the testes to produce sperm and then to produce testosterone. The interaction of luteinizing hormone and follicle stimulating hormone with the ovary is extremely complex. And we're going to discuss it in a little bit more detail. So if I can ever get this slide to change. There we are. Okay, so to discuss, the menstrual cycle occurs on average about every 28 days or so. It varies from person to person. As I said, it begins at puberty in females, and it lasts until a woman is anywhere between, some women earlier, as early as 35 or so, other women much, much later, at the age of 50, the menstrual cycle ends, it stops entirely, and the woman then becomes non-reproductive, unless she's given hormone treatments, in which case she can become reproductive again quite happily. Under normal circumstances, the reproductive phase of a woman is relatively limited given her whole lifespan. The end of it is called menopause. So let's first of all, let me point out what the menstrual cycle actually is. The menstrual cycle is the cyclic development and then shedding of a temporary layer of tissue on the lines the uterus. It is built up in response to the development of the egg, of the egg follicle, the ovarian follicle, in preparation for the receipt of a fertilized egg. If no fertilized egg is arises during that cycle, then this whole tissue layer is lost. It is shed. And that is the bleed of the menstrual cycle. That is the period. And this is a very carefully governed cycle. You must realize something, and that is this is a huge input. It requires a huge input of energy and everything else to build up this heavy layer on the inside of the uterus and then just lose it. So by and large, it is very carefully regulated. Unfortunately, things do go wrong. But by and large, it is carefully hormonally regulated. So we're going to date our events from day 1, which is the first day of bleeding during the period. This layer is called the endometrium. And the first day of the bleed, the endometrium is breaking down and is shed and is lost via the vagina during the period. And that can last 3 to 5 days, whatever. The bleeding will carry on. Again, there's a lot of variability. So this whole endometrium is lost down to a base layer. And then over the next little while, it is going to, I'm trying to move, I don't know if this is obscuring your view or not. Let me just do it. I'm trying to get rid of all of these bars and things, which are very annoying. Oh, no, sorry. Here we go. I just have to tell you, I guess. So, that'll do for the moment. Excuse me putzing around like this. There we are. Finally. So this breakdown here takes place. We leave a base layer here, and now from here on, the layer begins building up again and building up to a maximum. If no fertilized egg is received, then it breaks down again. And that overall is about 28 days. The bleed itself, let's say 5 days up till there, that is the uterine, called the uterine cycle. The uterine cycle is the cyclic buildup and loss of the endometrium. But lying behind that is a complex hormonal dance. So the very first thing I want to point out is that there is an ovarian cycle. While this is happening in the uterus, there's a cycle going on in the ovary as well. Here we have a follicle, an undeveloped follicle. The ovary is full of them. They were all developed when the fetus was in utero, and they're sitting there waiting. At the beginning of the menstrual cycle, there's a little battle, again, a hormonal battle that goes on between the follicles. But ultimately, usually only one wins and ends up developing, sometimes more than one. And then there is a possibility of non-fraternal twins being born. But the follicle begins growing. It's really important to note. This follicle not only contains the egg, it is in fact a little endocrine gland all of its own and produces its own hormones. And they are the hormones estradiol or estrogen and progesterone. So these two hormones are actually produced by the follicle, but they are produced under the influence of luteinizing hormone and follicle stimulating hormone that you've already heard of. Now, the way in which all of this interaction goes is extremely complicated. I'm going to simplify it radically for you and tell you that there is a positive feedback between these hormones, and its effect is really obvious. Look at what happens to the estradiol. It begins to get produced. It stimulates the production of more luteinizing hormone and follicle stimulating. That's follicle stimulating hormone. That name tells you exactly what it does. It stimulates the development of the follicle. These all talk to one another in a positive feedback. And after about 14 days, the production of luteinizing hormone especially peaks in very, very rapidly, in exponential fashion. And that peaking of the luteinizing hormone is what causes this ovarian follicle to actually burst and to release the egg. The egg is released into the fallopian tube, and it will spend several days tumbling down the fallopian tube. And if it gets fertilized, that is where it will get fertilized. It gets fertilized not in the uterus, but in the fallopian tube. And the fertilized egg then spends time tumbling down, ends up in the uterus, where it may bumble around a little bit. And in that interim, the lining of the uterus grows up as a fully developed endometrium, ready to receive this fertilized egg. So now we need to think about what happens under two circumstances. We'd say the fertilized egg, but what if the egg is not fertilized? In both cases, the next couple of days are basically the same. This ruptured ovarian follicle does not wither away and die, at least not immediately. Instead, it forms a new little unit, which is called the corpus luteum, right? What did we say here? Luteinizing hormone. The corpus luteum is this yellow body. And again, it is its own little endocrine system. Before the follicle secreted largely estrogen. The corpus luteum, however, secretes progesterone and estrogen as well. But progesterone is really the most important contributor here, because progesterone, together with the action of estrogen, but largely due to the progesterone, this endometrium develops. This endometrium develops under the influence of this progesterone. So the corpus luteum is what governs the development. Now, if an egg is fertilized and it settles here, then the fetus develops a placenta, which fixes to this endometrium. And the placenta itself is also an endocrine gland. And it produces hormones which maintain the corpus luteum. And the corpus luteum produces progesterone, and that is what maintains pregnancy. Now is the talk between the placenta and the corpus luteum, and then the hypothalamus and everything else. That's the one circumstance. The other circumstance is the more common circumstance, and that is that the egg is not fertilized. Well, it spends a couple of days bumbling around, but if it doesn't form a placenta, the corpus luteum begins to wither away. The corpus luteum is maintained by hormones from the placenta. If there's no placenta, the corpus luteum is not maintained. And after about 28 days, it withers away completely. And when that happens, all the progesterone and estrogen production stops. As soon as that stops, there's nothing now to hormonally maintain the endometrium. And the endometrium now breaks down and begins to be shed in the next menstrual cycle. And that again, that is day one of the bleed. There, we've come back to here. So the take-home message is that there is a very complex interaction of hormones, but we need to remember that we're talking about several different endocrine bodies talking to one another. We're talking about the follicle itself being one of them, largely producing estradiol. We're talking about the corpus luteum, largely producing progesterone. We're talking about the anterior pituitary producing luteinizing hormone, follicle stimulating hormone, under influence of hormones from the hypothalamus. And we're then talking, ultimately, if a fertilized egg settles, we're talking about the placenta being an endocrine gland as well to maintain the pregnancy. So if you want to revise this, there are numerous tutorials on this on YouTube, which you can use. And I think that is probably an easy way for you to make sure that you are clear on this. Now, those two hormones, the follicle stimulating hormone and the luteinizing hormone, both of them also govern the activities of the follicle stimulating hormone actually acts on a set of cells in the testes called the Sertoli cells. And the sperm are actually generated by another set of cells, but the Sertoli cells are actually responsible for maintaining the sperm cells through their development. They start off as relatively simple little cells. They are haploid, but they have no flagellum. When anything goes through a series of developmental stages, all of which are governed by the Sertoli cells. The luteinizing hormone regulates a set of cells called the Leydig cells, and they secrete testosterone. They also, by the way, secrete a little bit of estrogen, and there are a couple of others as well, and they promote spermatogenesis. That is, they get the initial, if you like, the mother cells that are going to produce sperm cells. They get them to divide, undergo meiosis, divide, and produce the sperm, whose development is governed by the Sertoli cells. Now, the testosterone, it goes into general circulation, and it has widespread effects throughout the body. It's not only on the gonads, it has effects on the development of muscle, all sorts of other things as well. That is the reason why people, for example, take illegal steroids if they're bodybuilding and everything. Because if you increase the levels of testosterone, you can increase bulk of muscle and that sort of thing. These, again, are regulated through a careful feedback loop. And they, for example, testosterone acts back on the hypothalamus and regulates the production of gonadotropin-releasing hormones, which in turn affects the follicle stimulating hormone and luteinizing hormone. But the anterior pituitary can also be directly affected by testosterone in a negative feedback as well. So here's just a simple schema for you. The hypothalamus produces gonadotropin-releasing hormones, which act on the anterior pituitary, which produce follicle-stimulating hormone. That acts on the Sertoli cells, and they govern spermatogenesis, the development of sperm. Luteinizing hormone acts on the Leydig cells, which produce testosterone, and that in turn acts on the cells which are going to produce the sperm, the initial divisions of the sperm. There are extensive feedback mechanisms. The Sertoli cells actually produce a substance called inhibin, and that can act directly on the anterior pituitary. But testosterone acts both on the anterior pituitary and on the hypothalamus to regulate levels of the hormones. Okay, so again, these are complex systems. You cannot hope to remember and to perfectly understand just at one hearing. What I have told you is the skeleton. You need to go and read and use as many resources as you can to get this clear in your mind. Okay. You do not, apart from the ones that I've set for you as homework or for you to revise on your own, you do not need to venture into the numerous others which are mentioned in your textbook. You can read them for interest, of course, but understand clearly the ones which I have discussed. And I will see you on Monday.